Hi, Rebecca. Can you hear me?
Yeah, I can.
Recording. And let me share with you this. So you were asking, how might you recognize what reaction is going to occur? So here you have an alkene and bromine.
Well, will there ever be multiple things happening?
Well, there could be. You could have this. So you would end up with this.
Sorry. Lower my volume.
Interesting ringtone.
I just got a new phone. I haven't set any of the preferences.
I was going to say it sounds kind of magical or something.
It's not terrible.
It depends. If you're like probably a guy who rides a Harley bike and that goes off in your pocket, you might get ridiculed. All right, but you see, this would be the reaction.
It's just the halogenation.
Yep. And if you're given this and H2O and you're told this is hydrolysis, what are you going to get? Well, it breaks right there. So there's the break. And see how I move them apart?
Yeah.
Okay, so what do you add to the carbonyl?
Was that the OH?
Well, let's try it both ways and see which makes the most sense. How's that sound?
Okay.
So you said, is that the OH? Well, we're going to try that. So what would go here?
The H.
Okay, now let's try it the other way. H here and OH there. Which one just looks more right? And why?
The top one.
Why?
Because the bond going from the carbon to the oxygen is where it was broken.
Well, yeah, it was broken, but I added an H there. Take a look at the products. What would you call this product as far as the functional group goes?
The carboxylic acid.
Okay, so I'm going to put Ca. What would you call this functional group?
An alcohol.
Okay, I'm going to put alk. What would you call this functional group?
Is that one aldehyde maybe?
It is an aldehyde. What would you call that functional group where you have an oxygen bonded to an oxygen?
Nothing.
Oh, it's a functional group. Have we talked about that one?
I mean, an alkane?
Nope.
Oh, that's a C to a C.
Yeah, this is an oxygen to an oxygen. Have you seen that before?
I want to say no, but the way you're phrasing it, just an O2 maybe.
Well, O2, it's oxygen double bonded to oxygen, and there's no hydrogen attached to it, and there's no carbon. Have you seen that before? The answer is no, you have not.
Right.
So what makes more sense, that this would break apart into two things that we've talked about before, or two things, or one you've talked about before and one you just have no idea what it is?
Right. That makes sense.
So I got to go with this way. You with me?
Right.
So that's what you do. You could do the same thing here where we say we're going to hydrolyze this. Now, often during these hydrolysis things, we add sodium hydroxide, but that's not a reactant. It's the spoon. Did we talk about the spoon before?
The catalyst.
That's right. So it doesn't get used up by the reaction, but it helps the reaction along. So where's this going to break?
In
right
between
there.
the
It
C
always
and-
breaks between this carbon right here and whatever is bonded next to it that's not carbon, right?
Right.
Okay, so I split it apart and I'm going to give it some wide berth here. So what do I
Okay.
add to each side?
The OH to the carbonyl and the H to
Well,
make
that's what you would think.
NH3.
Let's take a look. Let's take a look. So you want this here and this here, right?
Yeah.
Well, let's do it the other way. So what would you call that?
Uh, carboxylic acid,
Great. What would you call that?
the amine,
Okay. What would you call that?
the aldehyde,
What would you call that?
nothing.
You have no idea.
Okay.
It is a functional group. Nitrogen bonded to an oxygen like this is a functional group. So what is it? You have no idea.
Right.
So what's more likely, these two things that you would recognize or not?
Okay.
And to boot, you should know this reaction. What happens here?
Salt and water.
No,
So it's a
that's right. That will happen too. That will happen. But
so
if
it's
I
the
ask you to make,
carboxylic acid and the
if I
amine.
talk, if we talk about condensation, so yeah, this would be an acid-base reaction, but it's also a condensation reaction.
But it makes an amide and water.
Okay, so what's an amide?
It's the double bonded oxygen with the CN.
So like that, right?
Yeah.
And then it's CH3. There's the hydrogen, and what do these make?
Water.
So do you see that this above reaction is just the reverse of this reaction?
Right. But when it's the acid and the base,
When it's an acid and a base, so let's say that we want the acid-base reaction, we would write something different. We would do this. Okay,
so you took the H off of the acid
right, because it
and now
it
it's as a
donates
negative.
proton.
And the negative's the formal charge of the oxygen now?
That's right, because it's actually got 3 lone pairs, which would be a negative formal charge, wouldn't it?
Uh-huh.
Remember, formal charge is equal to group number minus the lone pair electrons and minus 1/2 of the bonding electrons.
I just
So-
usually do that at 6, and since there's 7, it's a -1.
Okay, so this is the formula, and what I taught you was the real concept. The real concept is, yeah, it should have 6, but it's got 7. So it's -1.
Okay.
Uh,
But then the
a lot of
positive,
people like the formula better. So this one would be positive because it should have 5, but it's got 4, right?
because of the nitrogen, yeah.
Yeah. So the
Okay.
nitrogen is the +1. So you just kind of recognize them based on the reactions you know for everything. So if you look at the alkanes and cycloalkanes, you only know 2 reactions for these. There's halogenation, and here you need light, right?
Mm-hmm.
And then there is combustion. And then for the alkenes, you know that there are basically 3 reactions. One of them is addition,
That was just
Re-
the polymerization one.
No, addition is you're adding Cl2 or H2 or Br2 or H2O, where
Okay.
one goes on one carbon, one goes on the other.
Oh, on the opposite side of the bond.
Yeah,
Okay. And for the H2O, is it an H and an OH? Or
that's right.
two H's? Okay.
An H and an OH, because you can't do this. So what I mean by that is, imagine this is your alkene, and you add H2O. This is not a possibility.
So for the addition, it's pretty much halogenation, but with water too?
Or water or hydrogen.
Okay.
See this? I added half of the water to each.
Oh, I have them written down as different things. I have hydration, hydrogenation, and halogenation.
Yeah, but they're all addition reactions.
Oh, okay.
Take a look at this, right? So let's make this a real reaction and put Cl2. And so we'll put Cl here and Cl. We have two separate things, right?
Yeah.
And we put them together. What did we get? We got one thing. So what do you say happens when you take two things and put them together and make one? That's called an addition, right?
Right.
Okay, now how do we know there's a polymerization reaction? Well, you're told there's a polymerization reaction. Plus, with the polymerization reaction, you're given one reactant, and that is the alkene, right?
Right.
So you know it's going to be a polymerization if you're not given a Cl2 or an H2 or a Br2 or an H2O
Right.
or an F2 or an I2.
But it doesn't have to say like plus initiator. It can just be the alkene.
Well, if you look at what the book says, does the book ever ask you what is the product of this reaction, but there's no initiator? No, they don't. They just say, what's the polymerization reaction?
Okay.
Or this makes a polymer. Write out the reaction, right?
Okay.
The book makes no mention of an initiator. So that's just my little addition to what happens so that you kind of have a better understanding.
Okay.
What's the other reaction you can have with an alkene? Combustion. So here, this is an interesting one because you're going to take your alkene and you're going to add O2, which many people might think, well, O2 is like Cl2, so I'm going to add an oxygen to each carbon, but that's not the case.
That's the CO2 plus H2O. Products.
Oh, say that again?
CO2 plus H2O.
Correct. And then there's amines. They can accept a proton, right?
Right.
On the nitrogen. So the nitrogen goes from that to that, correct?
Yeah.
And there's the hydrogen that it got. And then there's the carboxylic acids, which can donate an H plus. So they go from this to that, right?
Yeah.
And then the carboxylic acids and alcohols can make an ester plus water. Carboxylic acid plus an amine can make an amide plus water. And these two reactions are definitely different, but they're the same reaction. They're condensation reactions, right?
Right.
Okay. And so how would you know that you're having a condensation reaction instead of an acid-base reaction between your carboxylic acid and amine? Well, hopefully the question would be, here's a carboxylic acid, here's an amine. What does the condensation product look like? Or if they wanted you to do the acid base and say, well, here's a carboxylic acid, here's an amine. What's the acid base reaction look like?
Okay. So
Or,
there
or,
could be multiple reactions with the same two.
or maybe you're asked, here's a carboxylic acid, here's an amine. What are the two reactions they can do? So what would the two reactions that carboxylic acid and an amine could do? What are they?
Condensation and acid base.
That's it.
Okay, and the condensation is when you take off the OH and the H and make water.
That's right.
And the amide.
And you know, when you think of condensation, what is condensation in a normal layman's term?
I mean, gas going to
No,
liquid,
no. Just in the normal everyday person's term. Oh, look,
water collecting
yeah.
on the outside of a water bottle or something.
Condensation is a bunch of water on the outside of a water bottle, right? Can you use that idea to help you remember that you're going to make H2O in a condensation reaction?
Yeah.
Why not? I mean, H2O liquid is condensation for most people.
And these acid-base reactions, it looks like when the amine is reacted with like hydrochloric acid, it just leaves a Cl minus. There's no water.
That's right. But, you know, with this acid-base reaction, between an amine and a carboxylic acid, there's no water. So here's a nice little acid. Here's a nice little amine. And when they react, you get this. So is there any water there?
No.
No.
Okay, so we just have to remember on the acid-base reactions to put the formal charge.
Absolutely. And over here, what's the last reaction you can have is the polymer where you make a polyester.
With the diacid and the diol?
That's right. And a polyamide.
And that was with the diacid and the diamine?
That's right.
Okay.
And so with these reactions, you should also know the reverse.
Mm-hmm.
You know, what happens when you take them apart?
And the only one that requires the catalyst is the hydrolysis?
Not really. The backwards requires a catalyst too.
So the condensation and hydrolysis do?
The forward requires a catalyst too. Usually the forward is an acid catalyst and the reverse is a hydroxide catalyst. So here, usually this is the catalyst for the forward and this is the catalyst for the reverse.
So to go from the ester and water to a carboxylic acid and alcohol, you need the OH catalyst?
Now, our book doesn't talk about these things, does it? So don't worry about it. You know, if you're asked to make the condensation product, then don't worry about the catalyst. And if you're asked to hydrolyze it, don't worry about the catalyst.
Okay.
Because the problem is saying, hey, this can hydrolyze. What do you get?
Okay.
Because if I told you the real story, you'd start freaking out.
Mm-hmm.
You want the real story?
No.
Okay.
No, I don't.
Good choice. It turns out that when we have a regular semester, we do the real story because we do the real hydrolysis. And we do a real making an ester. So unfortunately, we can't do this online because it requires some very nasty chemicals, but there is a chemical that looks like this. And it's called oil of wintergreen. Now we add H2O and we add a catalyst. What's the hydrolysis product? So you thought this was a silly story, but no, I'm making you do some work now.
Um,
I'm not asking you to name the product. I'm asking you to draw it. Draw the product.
we have an ester, an alcohol, and water.
Right. So is the water going to react with the alcohol? Have you seen that reaction before? Have we done any reactions where it reacts with an alcohol?
No.
Okay, then don't worry about that.
So it's the ester and the water will react together.
So what are you going to get? Can you draw the two things you're going to get?
You're gonna break off.
Okay. Take a shot and draw it. Tell me when you.
Well, I'm assuming that I'm gonna get a carboxylic acid sort of ring thing and an alcohol.
Well, just draw it then.
Okay.
Take a chance, draw it. The worst thing that can happen is that you're wrong. And it's not lethal. Tell me when you're done.
Okay.
You're done?
I don't think I'm right at all.
So this is where it's going to break. So let me draw this after it has broken. So there's the break. Everything else is exactly the same. Now this part over here, you see how that kind of goes up? So I'm going to do that. So there's the break. Are you okay with that?
Okay.
What am I going to put on the left side of the break?
On the left side, you're gonna put an H.
Okay. And then what am I going to put on the right?
Actually, maybe switch it around.
Oh, because you don't recognize an O bonded to an O, do you?
Yeah.
That's
So that should be an H on the right then.
right. Do you recognize an O bonded to an H like this?
Yeah.
Okay. Do you recognize an OH bonded to a carbonyl like this?
Yeah.
Okay, then that's probably what's going to happen. And then we take this and we actually add this to it. So this is just going to surprise the heck out of you. And it reacts here. Not here, here. So take a look. What is this? A carboxylic acid, right?
Right.
What is that?
An alcohol.
So what happens if we have a carboxylic acid here and a carboxylic acid here? How do carboxylic acids react with one another? Well, they don't. But can carboxylic acids react with alcohols?
To make an ester and.
So what's the ester look like?
Well, we'll keep the double bonded oxygen to the carbon.
Circle the things that combine to make water.
The OH and an H.
Okay. Have you ever seen me do that when I'm trying to figure out what the product is? I circle the things that become water.
Uh-huh.
What do I do with the leftovers?
Put them on either side.
Stick them together, right? So here, you see this little lima bean thing here?
Uh-huh.
I'm going to combine it with that. So it's going to look like this, and it's going to look like that, right?
Okay.
So here's the lima bean thing. That's the lima bean thing, right?
Uh-huh.
So what do I put down here? This. Does that look like an ester?
Yeah.
And this here is called salicylic acid, which is the same thing here. And we make this thing here, which is called acetyl salicylic acid, but it's got a trade name, and the trade name is called aspirin. You ever heard of aspirin?
Oh, yeah.
Yeah, we make aspirin in this class when we meet face to face.
Oh, cool.
Yeah, and unfortunately, we can't really make you do it at home because it's too difficult and too dangerous.
So the functional groups in here, would there be an aromatic since there's the ring or no?
Yes, absolutely. There's an aromatic, an ester, and an alcohol. And here there's an aromatic, a carboxylic acid, an alcohol, and another alcohol here.
And it makes sense in the oil of wintergreen, but I guess the salicylic acid, you don't think that would smell?
Well, let me ask you this. Do solids really smell?
No, I guess it's the liquid in them.
No, liquids don't even really smell.
Well, the bacteria smells and it thrives in a moist environment.
But that's different. So what's happening there is that the only things you smell are gases. I mean, let's think about it. What do you smell with?
Your nose, it
Your
doesn't
nose.
smell
Are you sticking
liquids.
solids in your nose?
Right.
I hope not, because when I was a kid, I used to, and I used to get things jammed in there, and it was a problem. Do you stick liquids in your nose on purpose?
No.
No, but you've accidentally snorted water when you were swimming, right?
Yeah.
And did it smell good?
It hurt.
It hurt. You didn't smell a darn thing. You don't smell liquids. So what is it that you smell? Like when you, let's say that you drink wine, and you always see those people who are connoisseurs of wine. They swirl it, and the reason they swirl it is because they want to smell it. So when they swirl it, then they stick their nose in there, and what they're really doing is they're covering a lot of surface area of the glass with wine, and it makes more evaporation happen. So when it evaporates, not only is H2O evaporating and alcohol evaporating, but so are molecules that have odor to them. And a lot of molecules that have odor to them are aromatics, but a lot are not. So aromatic is a misnomer because it doesn't really necessarily mean that it smells. So when you swirl a wine, you get all these gas molecules being made, and that's what you smell. So can you smell aspirin? No, you can't. That's why, even though this is an aromatic, you can't tell because it's a solid. Salicylic acid is a solid. Why can't you smell that? Because it's a solid. Oil of wintergreen is actually a liquid. So why can you smell that? It turns out that it turns into a gas fairly easily, and you're smelling the gas molecules. Are you with me there?
Yeah.
Okay, so now you just learned how your nose works. If it if it's not a gas, you don't need to worry about it. But lots of things are gases, so, right?
Yeah.
All righty. So this is, something that you should kind of be able to do or understand at least. So let's say you take aspirin. Have you ever heard of something called a medicine cabinet?
Yeah.
And where is the medicine cabinet?
Usually in someone's bathroom.
In someone's bathroom. And what else do you do in the bathroom that gets really warm in there when you're doing it?
Shower.
Shower. So a shower puts a lot of H2O into the air, right?
Yeah.
So here's your aspirin in your hot shower room, and you store it in the medicine cabinet because that's where the medicine cabinet is. What's going to happen to your aspirin over time?
Well, is it hygroscopic or whatever?
Well, we're talking about reactions here. So,
Oh, so we're adding the water. The plus H2O is from the gaseous water in the air.
right, because you know that because it's hot, a lot of that H2O turns into gas. And you know H2O turns into a gas without boiling, because what happens when you put a little spot of water on your table and don't wipe it up? Does that spot stay there forever?
No, it evaporates.
Even though it's not boiling?
No, it'll evaporate.
Right. So that's my point, is that you don't need to have water boil to turn it into a gas.
Right.
Okay, so you got this gaseous H2O, and it helps even more if you warm up the water. Which, with a shower, most of us take warm showers and not these, room temperature showers. So what's going to happen here?
We're gonna take the OH off and the H from the water.
Oh, okay. So you're going to take this off? Let's do that. So we're going to break that. You see how I broke that?
Yeah.
Okay. What do we add to the carbonyl?
The OH.
Okay. And what do you add to the OH, or the oxygen on the other side?
An H.
Okay. So can you see that what you've done is nothing?
Yeah, it's the same thing.
Okay. So this probably does happen, but really nothing happens. Is there anything else that this can react in? Have we talked about the reactions of H2O with aromatics?
We've had.
Let's see. Let's take a look here. Here's our list of reactions we talked about. Alkane, cycloalkane, alkene, amine, carboxylic acid. I don't see any reactions with aromatics. Do you?
No.
Okay, so probably because they don't happen very easily. So I'm going to ask you again. Have we talked about any reactions of H2O with aromatics?
No.
No. How about H2O with esters?
Yeah, the carboxylic acid and alcohol.
So where is this going to break?
The carboxylic acid should.
There is no acid. The acid is up
Oh,
here.
the ester.
We did that one and it didn't do anything.
So we should break the ester off in between the oxygen and the carbon of the, I think. Shouldn't we break the ester off in between the double bond and the oxygen?
This double bond and this oxygen, or this double bond and this oxygen?
The second one.
This one? So
Yeah.
right there?
Yeah.
Just like we did up here?
Yeah.
So do you see a common theme here? when this is bonded to something other than carbon, what happens to it a lot of times?
You break that bond.
You break that bond. Okay.
So I should break the bond to carbon then?
So we're going to break that bond.
Oh, so I got it right.
Have we done it the other way? Have we ever done that?
No.
No. So we're not going to start now because it doesn't happen very easily. That's a very, very hard bond to break. Okay, so there's one piece. And there's the other piece, right?
Yeah.
So what do we add to which piece?
The OH to the carbonyl.
So we can do it this way, or we can do it this way, right?
Yeah.
No matter whether we use a HO or an O, it still works, right?
Right.
So here, this is the Christmassy product, ho, ho, ho. And this is the surprise product, oh, oh, oh. You with me?
Mm-hmm.
All right. Now, what about over here? What are you going to add?
An H.
So I'm just going to do that. So guess what happens when you leave aspirin in your medicine cabinet? It hydrolyzes.
Okay.
You don't leave meth. In fact, a lot of medications hydrolyze in your medicine cabinet because of the moisture.
Mm-hmm.
So if you don't want, and you know, the hot air helps that, right? So where should you really be storing your medicines?
In a cool, dry place, like it says on the bottle.
Where's that?
I mean, in your closet, under your sink in your kitchen, if there's no leak. I don't know.
In your refrigerator.
Oh, really? In your fridge?
Yes, your refrigerator is a dry place.
And it's constant temperature.
And it's cool, isn't it?
Yeah.
Why do you put things in your refrigerator anyways?
To preserve them.
So if you're trying to preserve your medicine, doesn't that sound like a great place to put it?
Yeah, I put probiotics in there. It makes sense.
Yeah. And if you don't need to worry about it freezing, where might you put it?
In the freezer.
In the freezer. So with a lot of medications, which are solids, you don't need to worry about them freezing. So you stick them in the freezer.
Okay.
Now, what do you have to be careful of when you thaw them? Well, in Humboldt County, when you thaw something, what happens to the outside of the container?
It condensates.
Condensation, because the humidity from the air hits the stuff, cools down, and condenses. So if you take anything out of the freezer, you need to worry about condensation. But as long as your container is well sealed, it shouldn't matter. So this happens with a lot of medications. Keep it in a cool, dry place so it doesn't hydrolyze. Bet you didn't know that, did you?
No.
Now you do. So if you ever want to just do an experiment just for fun, if you have any old aspirin sitting around, crush the tablet up into some fine powder, put it into a shallow cup, and then add just a little bit of boiling water to it, just a little bit, not too much, and smell it afterwards. What do you think you're going to smell? Well, you're not going to smell salicylic acid because it's a solid, but this is acetic acid. Acetic acid can turn into a gas fairly easily. So if you smelled acetic acid, what do you think what would pop into your head? Well,
vinegar.
Vinegar. So if you smell that tablet after you put it in the hot water for a little while, it's going to smell like a faint odor of vinegar coming off of it. And in the chemistry stockroom, we've actually had bottles of aspirin that were like 30 years old. And you open them up and you can get a faint whiff of vinegar. Now, what happens if you keep that bottle open too long? All the vinegar escapes and doesn't smell like vinegar anymore.
And the open, that if it's open, it's diffusion, the bottle. If you just open it up all the way.
Yeah, that's diffusion. And this right here, it turns out that this does everything that aspirin does. Aspirin is an anti-inflammatory.
Mhm.
So is this. Aspirin is an anticoagulant. So is this. Aspirin is an analgesic.
Mhm.
Analgesic. Trying to spell out. And so is this. And aspirin is also antipyretic. Do you know what that means?
No, I haven't heard of that.
Think about pyro. What is that?
I would say fire.
So what would antipyretic mean?
I mean, doesn't heat or something?
Okay, so what do we mean by anti-heat for a person?
Anti-fever.
That's right. So aspirin's got all these things going for it. It's an anti-inflammatory, it's an anticoagulant, it's an analgesic, and it's antipyretic. So does salicylic acid. Do you know where you find this stuff?
Acne medication.
Yes, but you find it in willow bark.
Oh, okay.
So Native Americans and probably other people too used willow bark as a remedy for toothaches and other things too, fevers. And you would just
Willow bark tea can be used to like jumpstart rooting too.
rooting.
Yeah, on plants.
Oh, okay. But so willow bark is this great little thing. The problem with this is that it can give you an upset stomach because of the acid. And interestingly enough, the acid is not this so much as it is this.
And does the hydrolysis of it affect the shelf life too?
Well, if it hydrolyzes, it's not aspirin anymore, it's salicylic acid. So what do you mean by shelf life?
I guess it's something different.
Yeah. So aspirin is good forever because when it hydrolyzes, you make salicylic acid, which still works.
Wow.
But you might get a stomach ache and maybe even ulcers.
Yeah, if you take it enough.
So that's why aspirin is better. And aspirin is not a natural product. It's made from a natural product, but it's not natural. It's synthesized, it's man-made, it's not natural at all. And the reason they came up with this is because it looks like that, but it doesn't cause as many stomach problems. And if you know anything about aspirin, a lot of people don't take it because it causes them stomach problems.
Mm-hmm.
But it doesn't cause as many people stomach problems as this would. So
Yeah.
aspirin is quite good. And now there's even other things that are even better that don't cause stomach problems that you can take, like ibuprofen, naproxen, things like that.
So will we be expected to draw like the unhybridized p orbitals on our line drawings?
You might have to show how pi bonding occurs because that's part of valence bond theory, right?
Yeah.
So yeah, you might have to.
Okay.
And just a quick way to do that is you do this, right? And there's your pi bond.
But if there's like one of those benzenes, you know, with the...
Well, that's even easier to do. You do this. So do you know why those two are close together and those two are far apart?
Just point of view.
Yeah, because those are far away, so they look like they're close together. And what happens with these on top, they overlap. What happens with these on the bottom? So I'm going to use a different colored pen for the ones on the bottom. They overlap.
And are there like 6 electrons on each side?
No, 6 electrons total.
Okay.
So you can almost think of it as like being 1 electron here, 1 electron here, 1 here, and then down here, 1 here, 1 here, and 1 here, kind of opposite of each other.
Mm-hmm.
And it's a lot better. You know, when you look at the real estate here, you got this big donut for the electrons, right? And this big donut down here for the electrons, right?
Yeah.
If you think about the double bonding being like this, so if you think of the double bonding as being more like this, where that's a double bond, double bond, double bond, then you might have this, and here's 2 electrons, and you have this, and here's 2 electrons, right?
Yeah.
And then you have this, and here's 2 electrons. Can you see that there's all this space where the electrons can't be between these 2 carbons?
Yeah.
And between these 2 carbons, there's all this space where the electrons can't be. And between these 2 carbons, there's all that space. So if we look at it from the top, we're saying that there's 2 electrons here, 2 here, and 2 here, but there's none here, here, or here. If we look at this from the top, we're saying that the electrons are spread out basically like this, nice and evenly between all 6 carbons. You with me?
Uh-huh.
What's going to be better, to be able to spread those electrons out over all that space, or to spread them out only between half of the space?
To spread them out like the donut.
Yeah, because they don't like each other.
Mm-hmm.
What do you do with unruly kids that don't like each other? You separate them. You don't send them to gladiator school and stick them in pairs and find it out, right?
Right.
Sometimes that's your only option, though. But here, that's not an option. You can actually spread them out, which makes this uber stable. Which kind of makes me wonder, why did they call it uber? Doesn't uber mean very? Why is it called an uber? Very?
Mm.
That doesn't make any sense.
It must be derived from, I don't know, something different.
I don't know. Uber means very.
I wonder why the company would have used it.
Well, probably because very is a better name than hardly ever, right? Would you like a ride? Hardly ever. Nope. Okay. What can I help you with?
Really, I think for me, it's just focusing more on these reactions.
I would do this then. So I'm going to open my book. And what I would suggest you do here is start doing some of these reactions that, where we have been doing reactions. So for instance, I'm just starting at the back of the book, and I'm going to work forward. So let's see here. Oh, they just got to, here, check your understanding. So here they have this problem, functional group chemistry, and they ask you all these problems. Reactions that you don't need to know, you should just ignore. Like here, what is the reaction of 2-butanol with an oxidizing agent? Did we do that?
I mean, if it's O2.
That's not what they mean.
Okay.
So it's not O2. It's like potassium permanganate. How about A, reaction of propanoic acid and 1-propanol? Well, what is propanoic acid? What type of molecule?
Propanoic. It's an acid.
It's a carboxylic.
Carboxylic acid, and we've got an.
How about what type of molecule is 1-propanol?
So the carboxylic acid in alcohol is the ester in the water.
You can make an ester in water. So here, take a look at A. Here's their solution. Here's propanoic acid. Here's your propanol. Here's your ester. Now, here's the one with the oxidizing agent, which we didn't cover because I thought that's just too much detail for this class. So here, look at these. We've got name these compounds, and then B, name the product of 1 and 2. So 1 is an alcohol, 2 is an acid. What are you going to make?
An ester and water.
Okay, what is the name of the structure with oxidation? Okay, we're not going to worry about that. How about combining 2 and 3? Acid and amine, what are you going to make?
An amide and water.
So you should be able to do that. And it says, what is the result of adding acid to compound 3? Should you know that one?
An acid to an amine.
Yeah.
That's the H2O and amide.
No.
The acid, a carboxylic acid to an amine, or like a hydrochloric acid?
Acid to number 3.
We're gonna get a plus charge on the N and a minus charge on the Cl.
Okay, so you should be able to do that, right?
Yeah.
And then after you do this, what you're going to do is you're going to flip to the back of the book. You're going to see that this is 23.7. Let's see if I can find it. Okay, 23. This is 22. 23. And here's 23.7. Oh, that's from the back of the book. So probably I have to go forward a little bit more. And this is answers to check your understanding. So now let's look for 23.7. Almost there. Okay, here's 23.7. So they say that you're going to get, with the amine and hydrochloric acid, you're going to get this guy here.
Would you zoom out just a little bit?
Oh, you're going to get that guy there. So do you see how you have 3 hydrogens bonded to the nitrogen?
Yeah.
And the reason they don't show the little plus charge there is because that is a cation. And guess what the chlorine is?
An anion.
Anion. So this is just the formula of an ionic compound, and you don't show charges when you show that. And look, didn't you say that for D, you're going to get an amide?
Mm-hmm.
So there it is. And didn't you say for A, you're going to get a, or for B, you're going to get an ester. So that's what that is. Okay, so what I would suggest is you try and pick out some of these and give them a shot, but also go to the back of the book. And here I'm going to skip to actually, I'm going to skip general questions. Should you know any reactions with alkanes and cycloalkanes?
Combustion and halogenation.
Okay, so here I'm taking a look here. And you see, let's see, draw the Lewis structure, blah, blah. Write a balanced equations for the following reactions. So should you be able to do 26?
Methane with excess chlorine. Yeah, that's a halogenation.
Right. And how about here? Uh, 20, I'm looking at alkenes and alkynes. Hydrogenation, should you be able to do that one?
Number 36.
Yeah. What do you think hydrogenation means?
To add H2.
There you go. Here, dichloropropene. That's not a reaction. Here, this is a reaction. Should you be able to kind of figure this one out?
So it's an alkane.
Actually, it says that it could be a cycloalkane or an alkene. How would you tell the difference?
I mean, if there's double bonds,
Right. How would you tell?
the Lewis structure.
This is a colorless liquid, so it's not going to tell you its Lewis structure.
So you would tell by putting a halogen in there and without light. And if it
Not just any halogen.
bromine, because it's brown.
That's right.
Br2.
Brown liquid.
And if there's no light and it changes color, it's an alkene. If there's light, if it needs light to change color, it's an alkane.
That's right. Or a cycloalkane, right?
Right.
So you go through and do all these problems here. Aromatic compounds. Do you remember the reactions we talked about with aromatic compounds?
There weren't any.
Okay, then skip that one. Okay, alcohols, ethers, and amines. Did we do any alcohol reactions with alcohols or amines?
Yeah.
Yeah, we did condensation reactions, didn't we?
Yeah, we did hydrolysis too.
And also we did acid-base things with amines, right?
Yeah.
So number 51, that's an amine and that's an acid. So should you be able to come up with a product?
Yeah, we'll get a.
And how about B?
Yeah.
So this is how you practice those reactions. Just go through there, find things that are reactions that look like you've done something with them before and do them.
And these hydrolysis, condensation, and acid-base reactions, you always break the carbonyl at that point.
Carbonyl to either oxygen or to nitrogen.
Right.
But not carbonyl to carbon.
So if there's like a ketone, where does it break?
Nothing's going to happen.
Nothing's going to happen. Well, we haven't seen anything with the ketone, I guess.
Yeah, nothing's going to happen.
Okay.
It's just going to sit there and laugh. It's going to go, you want me to do what? I'm on vacation.
It's hard to remember the acid-base one because the products are different than what we're used to.
Well, we did kind of do the acid-base stuff where an H goes from one molecule to another, and it's just the same thing.
Right?
And we call those Lewis acid bases. Do you remember that?
Yeah.
So it's the same thing. It's just
wait, the Lewis or the Bronsted-Lowry?
Oh yeah, we call those Bronsted-Lowry. I'm sorry, you're right. So we have done those.
Oh, okay, but we were just using water as the acid or the base.
We did. We showed how water could be a Bronsted-Lowry acid or a Bronsted-Lowry base, but you didn't need that.
Mm-hmm.
But in that chapter, we did usually use water.
Okay.
But that's the beautiful part really about the Bronsted-Lowry acid bases. You don't need water for that to be an acid or a base.
It's just the proton donors, the acid.
That's right, and the proton acceptor is the base. On the other hand, for an Arrhenius acid and base, you do need water.
Uh-huh.
Wow, this light makes me look like I've got bruising or something. Like an older person who bruises easily.
Oh, on your hands?
Yeah, it kind of looks like it. See how the shadow looks kind of bluish here?
Mm-hmm.
But when I turn my hand, you can see it's not blue. Maybe it's just that vein you're seeing.
So is the reverse of like a halogenation reaction, if it starts with the chlorines, is it also just a halogenation or like dehalogenation, blah, blah, blah?
Have we talked about removing halogens?
But you said it could go either way and that we might see it either way on the test.
I said we could go either way with hydrolysis and condensation, but I didn't say that about halogenation.
Oh, okay.
But what I did say about halogenation is that you should be able to know the reaction frontwards and backwards, meaning if this is your product, if this is your product, and I say this is an alkene, you better be able to draw it.
Mm-hmm.
So what's the alkene look like? Go ahead and draw it.
Okay.
You done?
Yeah.
Would you bet your bippy on it?
I'm pretty sure I would. Yeah, I should have then. I should have put all my money down.
All right. So that's pretty easy, right?
Right.
What if I say this? So what is this and what is that?
HCl should be plus HCl.
What's that?
Which one are you pointing at? Oh, the cycloalkane. It should be just a box.
There you go. So you should know these frontwards and backwards. Now, it turns out that you can actually do this, but I'm not going to tell you how.
Okay.
If you want to know how to go backwards, what do you have to do? You
You
take,
have to remove a chlorine.
you take organic chemistry at a university. That's what you do.
Yeah, I'm okay with what we're doing now. It's enough.
It is enough, but I got to tell you, there is something about organic chemistry that is, once you get into it, it's really cool.
Oh, I'm sure. I'm not surprised that there's a whole class on this chapter.
Oh, not, yeah, a whole 2 semesters.
Yeah.
Plus, you can go to graduate school and spend your whole graduate school on organic chemistry. And you're just looking at the tip of the iceberg. All righty, we're looking at 710.
Yeah, I think that's good to call it quits. I need to study more of these reactions anyway to actually make good progress.
Try more of those reactions. And if you want, also, there's a number of these Q&As where I'm doing problems that are reactions.
I just saw that. The last 2 you posted were just reactions, pretty much.
Well, those aren't problems, though. Those are just me throwing stuff up that people asked, that people want to know. What are the reactions we need to know? But the Q&As that say problems, blah, 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 and blah.
Okay.
You should take a look at those problem numbers and look at the ones in the book.
Oh, find the ones that are the reactions.
There's a couple of Q&As where I think I'm just doing reactions for people. Reaction after reaction after reaction. And here's how that can help you is you see, oh, Tony's doing reaction or number 72, and that's a reaction. I don't know if 72 is a reaction. But let's say you see, oh, he's doing this one and it's a reaction. You push play and you go, oh, stop. And you try and figure out the answer.
Right.
And then you push play and you go, oh, I was right. I should have bet my Bippy. You with me?
Yeah.
So that's the best way to learn is, see the setup, give it a shot yourself, see if you get the answer correct, and then move on.
All right, well, I will find those videos of the reactions and work more on them.
Okay.
So tomorrow it's Friday, so your last session is midday?
Yes, I'm not going to be working Friday nights. And
All
this,
right, well,
I've learned my lesson this summer. I'm not going to be doing 3 Zoom sessions a day.
yeah, that's a lot.
It's about 4.5 hours out of the day, it turns out.
Yeah.
Which means I don't do much grading.
I mean, it can't be the only work you have to do, yeah.
Yeah, and between trying to set up other things too, it's mind numbing.
Well, there's a lot of content now, extra content for students.
That's where I spend most of my time is trying to build content for you that you don't have to be with me in person. But I think you probably learned that there's a limit to how much you can do on your own.
Oh yeah, I think this is one of those classes that would be much better in person.
In my professional opinion, it is absolutely better face to face.
Yeah.
There's only the rare student who is able to do it online. And
it's really hard.
You're one of those rare ones. Charlotte, she's one of those rare ones, and Issa's one of those rare ones. But they're far between, few and far between. Online is not for everybody.
Definitely hard for me just to look at a screen this long.
Yes. And that's why when we're doing this, I try to put my little face up there so it seems like you're actually talking to someone. That way, maybe it's a little more real.
All right, Tony, well, you get some rest. Maybe some grading can get done. Just kidding.
Don't bet your Bippy on that.
All right. Well, thank you for being with me tonight.
Yep. Maybe we'll see you tomorrow if you can make it at one of those times.
I should be able to come midday, hopefully, if everything goes well.
All right. You have a good evening. Bye-bye.
You too. Bye.